Welcome to Educator.com. For today's Algebra 2 lesson, we're going to be discussing relations and functions. And recall that some of these concepts were discussed in Algebra 1. So this is a review, and if you need a more detailed review, check out the Algebra 1 lectures here at Educator. Beginning with the concept of the coordinate plane. The coordinate plane describes each point as an ordered pair of numbers, x, y. The first number is the x-coordinate, and the second is the y-coordinate. For example, consider the ordered pair -4, -2. This is describing a point on the coordinate plane with an x-coordinate of -4 and a y-coordinate of -2. Or the pair 0, 2. The x value would be 0, and the y value would be 2. So this is the point 0, 2 on the coordinate plane. Or 3, 5. X is 3, y is 5. Also recall that the quadrants are labeled with the Roman numerals 1, and then going counterclockwise, quadrant 2, quadrant 3, and quadrant 4. The coordinate pairs in the first quadrant, the x is positive, as is the y. In the second quadrant, you'll have a negative value for x and a positive value for y, such as -2, 4 would be an example. Third quadrant, both x and y are negative. And then in the fourth quadrant, x is positive, y is negative. And we'll be using the coordinate plane frequently in these lessons in order to graph various equations. Recall that a relation is a set of ordered pairs. The domain of the relation is a set of all the first coordinates, and the range is a set of all the second coordinates. Relation is often written as a set of ordered pairs using braces to denote that this is a set, and then the ordered pairs, each in parentheses separated by a comma. Sometimes the relation is represented as a table. So -2, 1, -1, 0, 0, 1, and 1, 2. We'll be doing some graphing of relations also in just a little bit. So as discussed up here, the domain is the set of all first coordinates. And the set of all first coordinates here would be -2, -1, 0, 1. The range is the set of the second coordinates. So the range right here, all the y values, 1, 0, 1, 2. However, you don't actually need to write the 1 twice. So in actuality, it would be written as such. So it's okay to repeat the values if you want, but usually we just write each value in the domain or range once each, represent it once. Okay, functions are a certain type of relation. So all functions are relations, but not all relations are functions. A function is a relation in which each element of the domain is paired with exactly one element of the range. For example, consider the relation shown 1, 4, 2, 5, 3, 8, 4, 10. So each member of the domain is paired or corresponds to exactly one element of the range. We don't have a situation where it's saying 1, 4, 1, 6, 1, 8, where that member of the domain is paired with multiple members of the range. Another way, again, to represent this as a table, another method that can be used is mapping. And mapping is a visual device that can help you to determine if you have a function or not by showing how each element of the domain is paired with an element of the range. So a map would look something like this. So over here I'm going to put the elements of the domain, 1, 2, 3, and 8. Over here, the elements of the range, 4, 5, 8, and 10. And then using arrows, I'm going to show the relationship between the two. So 1 corresponds to 4, or is paired with 4, 2 to 5, 3 to 8, and this should actually be 4, 4 to 10. Okay, so as you can see, there's only one arrow going from each element of the domain to each element of the range. And that tells me that I do have a function. Let's look at a different situation using a table form. So let's look at a second relation. In this one, I'm going to have -2, 2, -3, 2, -4, 5, and -6, 7. Now I'm going to go ahead and map this. -2, -3, -4, and -6. These are my elements of the domain. For the range, I don't have to write 2 twice. I'm just going to write it once. 5 and 7. Okay, -2 corresponds to 2. -3 also corresponds to 2. -4 corresponds to 5. And -6 corresponds to 7. This is also a function. So both of these are relations, and they are also functions. It's okay for 2 elements of the domain to be paired with the same element of the range. This is allowed. What's not allowed is if I were to have a situation where I said, I had 1, 2, 3, 4, 5, 6, and I had 1 paired with 4 and 1 paired with 5. So if you have 2 arrows coming off an element of the domain, then this is not a function. So here's 2 examples of relations that are also functions. There's a specific type of function that is called a one-to-one function. And a function is one-to-one if distinct elements of the domain are paired with distinct elements of the range. In the previous example, we saw a situation where we did have a one-to-one function and another situation where we did not. Okay, so to review, the ordered pairs in that first function that we just discussed were 1, 4, 2, 5, 3, 8, and 4, 10. Okay. And we can use mapping, again, to determine what the situation is with this relation, which is also a function. The domain, 1, 2, 3, 4. And the range, 4, 5, 8, and 10. When I put my arrows to show this relationship, you see that distinct elements of the domain are paired with distinct elements in the range. So 1 is paired with 4. They're each unique. Each pair is unique. Looking at the other function that we discussed, pairs -2, 3, -3, 2, -4, 3, slightly different, but same general concept, slightly different though. Okay. Here I have -2, -3, -4, and -6. Over here in the range I have 3, 2. I'm not going to repeat the 3. I already have that. And then 7. Negative 2 corresponds to 3. Negative 3 also corresponds, negative 3 corresponds to 2. Negative 4 also corresponds to 3. Negative 6 corresponds to 7. This is still a function, okay? So these are both functions. Function, function. However, this is a one-to-one function. This is not one-to-one. Because they're both functions, since each element of the domain is paired only with one element of the range. But in this case, it's not a unique element of the range. These two, negative 2 and negative 4, actually share an element of the range, whereas this is unique. It's a one-to-one correspondence. Okay, we can graph relations and functions by plotting the ordered pairs as points in the coordinate plane, as discussed a little while ago. There's a couple types of graphs that you can end up with. The first is discrete, and the second is continuous. So let's look at those two different types. Consider this relation. Okay, so if I'm asked to graph this relation, I'm going to graph each point. Negative 4, negative 2. It's going to be right here. Negative 2, 1, right here. Here, 0, 2, 0 on the x, 2 on the y. This is a discrete function, discrete graph, discrete relation. This actually is both a relation and a function. So it's a discrete relation or a discrete function. And the reason is because I have a set of discrete points. They're not connected. And I can't connect them because I haven't been given anything in between or a way to know if or what lies in between these. I can't just connect them when I don't know. There could be a point up here, point, or actually this is just the entire relation. So I can just work with what's given. Okay, a different scenario would be if I'm given a relation y equals x plus 1. And I can go ahead and plot this out. If I say, okay, when x is negative 1, negative 1 plus 1 is 0. When x is 0, y is 1. When x is 1, 1 plus 1 is 2. When x is 2, y is 3. Okay, so I'm going to go ahead and plot this out. When x is negative 1, y is 0. When x is 0, y is 1. When x is 1, y is 2. Let's move this out of the way. So when x is 1, y is 2. When x is 2, y is 3. Now, I have a set of points because these are the points I chose. But because I'm given this equation, there's an infinite number of points in between. I could have chosen, x is 0.5 to get the value 1.5 here to fill that in. And on until this becomes continuous and forms a line. So this is a continuous function. So the graph is a connected set of points. So the relation or the function in this case, since we do have a function, continuous relation or continuous function, because I have a line. Whereas this, just a set of points, is a discrete relation. Okay, one visual way to tell if a relation is a function is using the vertical line test. And a relation is a function if and only if no vertical line intersects its graph at more than one point. This is most easily understood through just working through an example. Consider if you were given the following graph. Okay. And the vertical line test, what you're seeing is, can you put a vertical line somewhere on the graph so that it intersects the graph at more than one point? And I can. I put a vertical line here and it intersects this graph at 1, 2, 3 places. Over here, it only intersects at one place. That's fine. But if I can draw a vertical line anywhere on the graph that intersects at more than one place, then we say that this failed the vertical line test. And when something fails the vertical line test, it means that it is not a function. The reason this works is that if 2 or 3 or more points share the same x value, then they're going to lie directly above or below each other on the coordinate plane. For example, looking right here, I have x equals 3. X is 3, y is 0. Then I look right above it, up here. Again, x is 3, and y is, say, 2.1, pretty close. Then I look up here. Again, x is 3, and y is about 4.6, approximately. So when x values are the same, but then the y values are different, that's telling me that members of the domain are paired with more than one member of the range. By definition, that is not a function. Okay, consider a different graph. Consider a graph like this of a line, a straight line. Okay. Now, anywhere that I pass a vertical line through, anywhere in this graph, it's only going to intersect at one point. So this passed the vertical line test. Therefore, this line, this graph, represents a function. Okay, so the vertical line test is a visual way of determining if a relation is a function. Okay. Working with equations, an equation can represent either a relation or a function. If an equation represents a function, then there's some terminology we use. And let's start out by just looking at an equation that represents a function. Okay. The variable corresponding to the domain is called the independent variable, and the other variable is the dependent variable. So here I have x and y, and let's look at some values. Let's let x be -1. Well, -1 times 2 is -2 minus 1. That's going to give me -3. When x is 0, 0 times 2 is 0 minus 1 is -1. When x is 1, 1 times 2 is 2 minus 1, y is 1. When x is 2, 2 times 2 is 4 minus 1 gives me 3. So looking at how this worked, x is the independent variable. So x is the independent variable. The value of x is independent of y. I'm just picking x's, and here it could be any real number. We sometimes also say that this is the input, and the reason is I pick a value for x, say 0, and I put it in. I input it into the equation. Then I do my calculation, and out comes the y value. So y, the value of y is dependent on x. Therefore, it is the dependent variable, and we also sometimes say it's the output. You put x in, do the calculation, out comes the value of y. So x is independent, y is dependent. Some notation that you'll see frequently in algebra is function notation. So we've been writing functions like this, y equals 4x plus 3. But you'll often see, instead of an equation written like this, if it's a function, you'll see it written as such. And when we say this out loud, we pronounce it f of x equals 4x plus 3. And we're talking about the value of a function for a particular value of x. So we say the function of f at a particular x. Let's let x equal 3. Then we can talk about f of 3. So the value of the function, the value of y of the dependent variable when the independent variable x is 3. And in that case, since it's telling us x is 3, I'm going to substitute in 3 wherever there's an x. And I could calculate that out to tell me that f of 3 is 4 times 3 is 12 plus 3. So f of 3 is 15. Here, x is an element of the domain of the independent variable. F of x is an element of the range. So again, we're going to be using this function notation frequently throughout the remainder of the course. Looking at the first example, the relation R is given by this set of coordinate pairs. Give the domain and range and determine if R is a function. Well, recall that the domain is comprised of the first element of each of these coordinate pairs. So in this case, the domain would be 1, 2, 6, 5, and 7. The range is comprised of the second element of each ordered pair. So I've got 4, 3, 4 again. I don't need to write that again. 3, I've got 3 already, and 5. So I'm just writing down the unique elements. So this is the domain, and this is the range. Now, is R a function? Well, I can always use mapping to just help me determine that. And I'm going to write down my members of the domain and my members of the range, elements of the range. And then I'm going to use arrows to show the correspondence between each. So 1 and 4, 1 is paired with 4, 2 is paired with 3, 6 is also paired with 4, 5 is paired with 3, and 7 corresponds or is paired with 5. Now I'm looking and I only see one arrow leading from each element of the domain. There's no element of the domain that is paired with 2 elements of the range. So in this case, this is a function. So is R a function? Yes. This relation is a function. R is a function. So always double check, make sure you've answered each part. I found the domain, I found the range, and I determined that R is a function. Okay, the relation R is given by the equation y equals 2x squared plus 4. Is R a function? What are the domain and range? Is R discrete or continuous? So let's just look at some values for x and y to help us determine if this relation is a function. So if I let x equal -1, -1 times -1 is 1, times 2 is 2, plus 4 is 6. Okay, if x is 0, this is 0 plus 4, that gives me 4. If x is 3, 3 squared is 9, times 2 is 18, plus 4 is 22. So as you're going along, you can see that for any value of x, there's only one value of y. Therefore, R is a function. So R is a function. Okay, what is the domain? Well, I could pick any real number. I could pick any real number for an x value that I want. So the domain is all real numbers. You might at first glance say, oh, the range is all real numbers as well, but that's not correct because look at what happens. Because this is x squared, whenever I have a negative number, it becomes positive. If I have a positive number, it stays positive, of course. Therefore, if I have, say, -1, that becomes 1, this becomes 6. So I'm not going to get any value lower than, for y, the smallest value I'll get is for when x is 0. Okay? So if x is 0, y is 4. Because negative 1 is going to give me a bigger value. It's going to give me 6. If I do negative 2, that's going to be 4 times 2 is 8 plus 4 is 12. So the lowest value that I'll be able to get for y will occur when x is 0. And that's going to give me a y value of 4. Therefore, the range is that y is greater than or equal to 4. So the most difficult part of this was just realizing that the range is not as broad as it looked initially. Because this involves squaring a number, there's a limit on how low you're going to go with the y value. So this is a range with the domain of all real numbers and a range of greater than or equal to 4. Okay. In example 3, graph the relation r given by 2x minus 4y equals 8. Is r a function? Find its domain and range. Is r discrete or continuous? Okay, so graph the relation given by 2x minus 4y equals 8. Let's go ahead and find some x and y values so that we can graph this. So when x is 0, we need to be able to solve for y. So when x is 0, let's figure out what y is. That's 0 minus 4y equals 8. Therefore, y equals negative 2, dividing both sides by negative 4. Okay? When x is 2, 2 times 2 minus 4y equals 8. That's 4 minus 4y equals 8. That's negative 4y equals 4. Y equals negative 1. Okay. And let's do one more. When x is negative 2, this is going to give me negative 4 minus 4y equals 8. That is going to then give me, adding 4 to both sides, will give me negative 4y equals 12, or y equals negative 3. That's good. All right, so when x is 0, y is negative 2. When x is 2, y is negative 1. When x is negative 2, y is negative 3. So right here. Okay, so I'm asked to graph it, and I have some points here that I generated, but I also realized that I could have picked points in between these, which would actually end up connecting this as a line. So I'm not just given a set of ordered pairs. I'm giving an equation that could have an infinite number of values for x, which would allow me to graph this as a continuous line. Therefore, I graph the relation. Is r a function? Is r discrete or continuous? Well, I've already answered that. Seeing the graph of this, I know that this is continuous. And let's see. Next step, is r a function? Yes, it is a function. Because if I look for every value of x, for every value of the domain, there's a unique, there's a value of the one value only of the range. So every element of the domain is paired with only one element of the range. It's continuous, and it is a function. Find the domain and range. Well, this is another case where I could choose x to be any real number. So all real numbers. It could be all real numbers, any real number. Here, the situation is the same for the range, all real numbers. Depending on my x value, I could come up with infinite possibilities for what the range would be, what the y value would be. So r is a function. It its domain and range are all real numbers, and this is a continuous function. Okay, in example 4, we're given f of x equals 3x squared minus 4 and asked to find f of 2, f of 6, and f of 2k. So first, f of 2. Recall that when you're asked to find a function for a particular value of x, you simply substitute that value for x in the equation. So f of 2 equals 3 times 4 minus 4. So that's 12 minus 4. So f of 2 equals 8. Next, I'm asked to find f of 6. And that's going to equal 3 times 6 squared minus 4. F of 6 equals 3 times 36 minus 4. And that turns out to be 108 minus 4. So f of 6 is 104. Now, at first, this f of 2k might look kind of difficult, but you treat it just the same as you did with the numbers when x is a numerical value. Everywhere I see an x, I'm going to insert 2k. And figuring this out, 2 times 2, so 2 squared is 4. K times k is k squared. 3 times 4 is 12, so I have 12k squared minus 4. So f of 2k equals 12k squared minus 4. So again, if you're asked to find the function for a particular value of x, you simply substitute whatever's given, including variables, for x. That concludes this lesson of Educator.com. I'll see you back here soon.